Hi everyone, welcome to Unit 4, Day 1. I am Mrs. Fisher. I'll be doing Unit 4 notes. And this time I'm not deathly ill, so hopefully I won't be hacking up along. And I'll try to talk faster this time so you guys don't have to watch me at 1.5 times speed. So we're going to start off with what trigonometry means, because this unit is on beginning trigonometry. Okay, so we're going to start off with the root word trigon, which means triangle. And then the second word here, metron, which means measure. These are both Greek words, so they basically mean that we are going to be studying the measure of different parts of a triangle. And we are going to be doing that with something called circular trigonometry, which sounds confusing, but basically we're going to be making triangles inside of circles. And today we're going to be talking about all the stuff you did in Math 3. So it's just a quick little review of everything you did in Math 3 done in one day. So there's a lot, which is why we give you a worksheet. So last year, we're going to start off with unit circle. And last year, we basically explored that idea on a Ferris wheel problem. And so we ultimately looked at a Ferris wheel with a radius of 1. And when we found out when you had this special circumstance with a radius of 1, then we could specifically refer to the sine of the angle as representing height, and cosine of the angle representing horizontal displacement. Okay, so if you were to plot the Ferris wheel on a set of x and y axes, you would know all of the coordinates of all of these points shown. So we are going to fill in all the degree values, the radian values, the different heights and displacements at all these different locations. Okay, so just starting here at 0, where we always start, we're going to do 0, and each of these segments that are this big, this many, is 30 degrees. So the easiest way to do this is to go in the 30-degree increments. You will eventually need to memorize this. So we're going to go 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and then when we get to full circle, that's 360. Fun fact, our circles have 360 degrees because ancient civilizations thought that there were 360 days in a full calendar. So our degree increment means absolutely nothing. They just thought a full year was 360, so we broke it up into 360. It also is a very convenient number, so we stick with it. These middle pieces here are 45 degrees, so we are going to now count those off. 45 plus 45 gives us 90 up here at the top, plus another 45 is 135, plus another 45 gives you the 180, plus 45 gives you 225. And then we get 270 and then 315. Okay, so we're just adding to get all the different angle measures. For the radian measures, we are going to do the same thing. We are going to add. We're going to start with 0 radians. And then we are going to start with our small segment, the 30-degree segment. This one is pi over 6. And we're basically going to be adding pi over 6 for all the 30-degree increments. Pi over 6 plus pi over 6 is 2 pi over 6. And 2 pi over 6 reduces down to pi over 3. So you're talking about 2 6 reducing to 1/3. If you just treat the pi like a variable like x would be, you have 2/6 pi reducing to 1/3 pi. The next increment would be 3/6, which reduces to 1/2. So it's 1/2 pi, which you can write as pi over 2. And we're going to count going on that way. So we have 3/6, then to 4/6, which reduces to 2/3. Then we have 5/6, which does not reduce. And then we have 6/6, which is 1, so 1 pi. Then we have 7/6, 8/6, which reduces, 9/6, 10/6, 11/6, and then 12/6 is 2 pi. And then all the 45-degree increments are multiples of pi over 4. So we have pi over 4, 2 pi over 4 brings you to 1/2, 3 pi over 4, 4 pi over 4 is pi, 5 pi over 4, 6 pi over 4 is this one, and then 7 pi over 4. So again, we're just counting 8 pi over 4 would be 2 pi. So we just count all of those. And then all the coordinates we got last year by simply making 30, 60, 90 triangles in inside this circle. So I'm going to go ahead and fill all those out. We have 1, 0. And then if we made a little right triangle inside of here, we have this little triangle. It was a 30, 60, 90 triangle. And we used those properties of a 30, 60, 90 with the radius here being 1. And then we said this bottom side is going over √3/2, and this is going up 1/2. So that's how we found all of our coordinates, is just manipulating those triangles. So we get √3/2, 1/2. And then did the same thing with a 45, 45, 90. This is √2/2, √2/2. And then 1/2, √3/2. And then 0, 1. And all the other angles are just manipulations of those. They're just in different quadrants. So this one over here is -1/2, positive √3/2, negative √2/2, positive √2/2, and then negative √3/2, positive 1/2. So this should be reflections of what you see in quadrant 1. And then this is -1, 0. Then the bottom quadrant, everything is negative. Because you're going to the left and down. And then down here, we're 0, -1. And then quadrant 4, again, you can think about reflections. We're going to the right and down, so you should have positive x coordinates and negative y coordinates. Okay, so that is your unit circle. And like it says down here at the bottom, the values for quadrant 1 need to be committed to memory. And you're going to be using these. We used them last year in Math 3. We're going to use them again this year. In pre-cal, you'll be using them next year. Unless you're just taking AP Stats. But you're going to be using them next year. So you do need to commit them to memory. We're going to have multiple quizzes on this beginning next class. So next class, the quiz is just on quadrant 1. And by next class, I mean day 2. So that's actually day 2. On day 2. All right. All this other stuff that says positive, negative, they want to know what is positive in quadrant 1, what is negative. In positive, we have cosine values and sine values are positive. Nothing's negative in quadrant 1. In quadrant 2, we have positive sine values, and negative would be the cosine. In quadrant 3, positive, we'll come back to in a second. Negative, we have cosine and sine. And then in quadrant 4, positive, cosine, negative, sine. All right, so come down here. Do you recall SineCosine? I hope so. Some old hippie caught another hippie tripping on acid. Is one way you can remember it. My teacher used to talk about horses and oats and stuff. Anyway, sine is the O and the H, so that's the ratio of the opposite side in the triangle over the hypotenuse. Cosine is the ratio of the adjacent side of the triangle over the hypotenuse. And the tangent is the ratio of the opposite side of the triangle over the adjacent. Okay, so using that idea, what would be sine divided by cosine? So sine, if we have sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. If we look at that, then using the idea of a fraction divided by a fraction is keep, change, flip. We can do opposite over hypotenuse times hypotenuse over adjacent. Your hypotenusa cancel out, and you are left with opposite over adjacent. So, thus proving that sine over cosine is the same as opposite over adjacent, which is the same as tangent. So tangent would be the same thing as sine divided by cosine, which means up here under unit circle, you can use all of these lovely x and y values which represent sine and cosine. So again, x is cosine, y is sine. To also find tangent values. So if you know that sine is positive and cosine is negative in quadrant 2, that means that tangent would also be negative. In quadrant 3, if cosine and sine are both negative, if we divide them, we're going to get that tangent is positive. And in quadrant 4, if cosine is positive and sine is negative, that means that tangent would also be negative. All right, moving along. So we can use our unit circle to help us answer questions when we are asked to find the exact value. Some of you are confused what exact means. It means that you don't have a decimal for an answer. That means we're not going to use a calculator. So in this first example, it says find the exact values of sine of 45 times cosine of 60. So you want to go to your unit circle, look at the sine of 45, that's the y value, and the cosine of 60, that's the x value. So go to 45, look at the y value, that's this. That's root 2 over 2. Cosine of 60, so go to cosine of 60. That's the x value. That's 1/2. And you're going to multiply those together, and you get root 2 over 4. So that would be the exact value for that problem. In example 2, it says find the exact value of tangent of negative 11 pi over 3. So this one's a little bit tricky because 11 pi over 3 is not expressly written on the unit circle. A couple things here. We've got a negative sign, so that means that you need to go backwards on the circle. We talked about that last year. And 11 pi over 3 means you need to work 11 sections of pi over 3. Okay, so let's move back up to the unit circle. One section of pi over 3 is this big. And I'm going down because it's negative, so I'm going backwards on the unit circle. So that's one section of pi over 3. I need to do 11 of those. So that's 1, 2, oops, I didn't mean to make it a straight line. If I hold my pencil too long, it makes it straight. So here's 2, 3, 4, 5, 6. So 6 pi over 3 is one full circle. So you can count that a lot quicker if you figure that out. So that's 6 pi over 3. I'm going to go around again. Seven pi over 3, 8, 9, 10, 11 pi over 3. And I've stopped right here at this spot. Now the question was to find tangent. Tangent means you are going to divide sine over cosine. That is y over x. Okay? So tangent is a y over x. So we are going to do root 3 over 2 divided by a half. And when we do the keep, change, flip, we're going to get root 3 is our answer. All right, arc length review. So we did arc length last year as well. This is all dependent on a radian value. Okay, so a lot of you are probably not going to remember where the heck radian came from. Radians are directly related to circumference of a circle when the radius of the circle is 1. So I have a little circle diagram over here for you, so let's just talk about that briefly. If your circle is 1, your circumference is going to be 2 pi times the radius, or pi times diameter, whichever one you want to think about. If you've got 2 pi times radius, that's your circumference. Pi times diameter, if your radius is 1, your diameter is 2. Either way you do this, the circumference of this pretty little circle I've given you is 2 pi. Either way. So the way that a radian value is defined is that it's going to be the size of the angle when you're related to the circumference when your radius is 1. So if you have this whole circle and this is your angle, the whole thing, and your circumference is 2 pi, then this angle across from it, that whole central angle, is going to be defined as 2 pi. Okay, so that whole central angle is 2 pi. So if you talk about an angle that is smaller than that, like what I've shaded in blue over here, so let's say that this shaded piece is only a quarter of the circle. So if that's a quarter of the circle, then what portion of the circumference do we have? Hopefully you said, you have a quarter. So this arc length right here that I've highlighted and is labeled S would only be a quarter of 2 pi, a quarter of our circumference. So we would get pi over 2. So they've defined a radian as being equivalent to that circumference value. So the circle, the central angle there, that theta for angle would be pi over 2. Okay, remember theta stands for an unknown angle. All right, so that angle is going to be pi over 2. So that brings us back to our original conversation, arc length. So if our circle is not a radius of 1, what's going to happen to our arc length? So if I made the circle bigger on the outside, what is going to happen to the arc length? So if I double the radius, what would happen to the length of the arc? Hopefully you said it doubles. So if it doubles, then the arc length doubles. If the radius triples, then the arc length is going to triple. So basically what happens is your arc length formula is going to be S for arc length. So S equals theta, your radian measure of the angle, times your radius. Now it's very important that you see that theta has to be in radians for this to work. And we did talk about this formula last year. This is not brand new information, hopefully. All right, so you can use this formula to find the missing information. So it's pretty straightforward. S is 4 pi over 3. Theta is what we're looking for, and R is your radius. So if I'm looking for the angle in this circle situation, you just need to divide both sides by 2. So you get 4 pi over 3 divided by 2 equals your theta. So that means theta is going to equal 2 pi over 3. In number 2, it says S equals theta times R. So we are going to have 11 pi over 4 equals theta times R. So we're going to divide both sides by pi over 8. So when we divide, we keep, change, flip. So I'm going to do 11 pi over 4. And I'm going to multiply by the reciprocal of pi over 8. And that's going to equal the R. The pi's cancel out. And you can reduce these two to a 2. So we get 22 equals the R. All right. Sector area formula we did talk about last year as well. So this one, I'm just going to write down for you. S equals 1/2 theta R squared. Again, theta must be in radians. If it's not in radians, this is not going to work out for you. Okay. So suppose you're trying to find the area of a sector with theta equals pi over 2 and R equals 4. Find the area, leaving your answer exact. All right, so, and let me change this. Don't do S, do area, A. Okay, so find the area. So we'll say area equals 1/2 times pi over 2, and then 4 squared. So that would end up being 16 for the 4 squared, and then pi, and then the 2 times 2 at the bottom gives you 4, so you get 4 pi for the area of your sector. And I just realized some of you might be saying, Ms. Fisher, what's a sector? A sector is like this blue shaded region up here. It looks like a piece of pie. That would be a really large piece of pie, but you're basically finding the area of a piece of pie. All right, so I want you guys to try, maybe pause the video, try, see if you can do these questions on your own. Let's see how you did. 1/2 theta in radians. And then radius squared. So you get 36 pi over 6. So that's 6 pi. And usually you would have some kind of units to write with that. So this right now is just units squared because it's an area. The second one, area equals 1/2 theta times radius squared. So that's 36 pi over 10, which reduces to 18 pi over 5 units squared. All right. We also talked last year about converting from degrees to radians and radians to degrees. We used a proportion for that. So, and some of you can figure out how to do this kind of thing in your head. I like having a proportion. So you would put your degrees over 180 equals radians over pi. You could also use, instead of 180, you could use 360, and instead of pi, you could use 2 pi. But it's basically a unit conversion, just like you know that there's 12 inches in 1 foot to use as a unit conversion. Okay, so it's just setting up a proportion. to do that. You could also do unit conversion similar to what you would do in chemistry. You could kind of set up a conversion like that as well. And if that makes more sense to you, then I can show you how to do that. I've just always done it with a proportion. Like this one, 6 pi over 7 is a radian measure. So you can set up the proportion. We want to convert it to degrees, so we don't know what the degrees are. So degrees over 180 equals the number of radians over pi. Okay, and then this pi and this pi cancel out, leaving you with x over 180 equals 6 over 7. And so to solve, you're just going to multiply the 180 over to this side. So x equals 6 times 180 over 7. And you're just going to type that into a calculator. And you get 154.3 degrees. And no, you should not just write that as 154. All right, for number 2, 67 is a degree measure that you know. Put that over 180. What you don't know is what that is in radians, so that's your x value. Put that as x over pi, and then multiply. Here, your unit, the degrees, cancels out. Multiply the pi over to the other side, so you get 67 pi over 180. If that is reducible, you want to reduce it. But 67, I believe, is a prime number. So you are going to leave that as 67 pi over 180. So that's your answer. All right, this last section, reviewing sine and cosine graphs. I've put the parent functions up here at the top. These are the no-shift mother functions. So you do need to know the difference between them. We've already looked at them back in Unit 2. Oh, sorry, I think that was Unit 1. Yeah, back in Unit 1, the second unit that we did. You do need to know the difference. Sine has the y-intercept at 0, 0. Cosine has the y-intercept at 0, 1. The key to graphing these things is understanding that there is a midline that's kind of key to everything here. So the midline, when it's a parent function, is right here at the x-axis. So for both of these, the midline is the x-axis. That midline is really important. Both of these are centered, what I call centered around the midline. If you look, you have a hill that goes above the midline and then a hill that goes below the midline. Okay? And it goes 1 unit above and 1 unit below. For cosine, the same thing kind of happens, except you only get 1 full dip below the midline, and then you get kind of like a half of a dip on either side here. Okay, but you're still going 1 above and 1 below the midline. So the midline is very important, and it's important to be able to identify where your midline is. That becomes really important later on in this unit. All right, so we're going to use that idea to help us with our basic transformations to graph, okay? So in number 1, it says graph sine x minus 2. So you want to take your mother function of sine, the minus 2, what does that do? Hopefully you said shifts it down 2. All right, so we are going to shift down 2. And what that means is that your midline is not at the x-axis anymore. It starts down 2. So we are going to start down 2. I know I'm making a dotted line. It is not an asymptote. It's just a point of reference for us. That is our midline. Okay, so we are going to put our y-intercept on the midline, just like it is in the parent function. Okay, then we are going to go up 1 at pi over 2, just like it is in the parent function. And then at pi, we're on the midline again. And then at 3 pi over 2, we're down 1 from the midline. And then at pi, or at 2 pi, we're back to the midline. So there's your sine graph. And this is all on our y-axis 1 unit. So when I say label your axes appropriately, this is what we're talking about. If you want to do more than 2 unit or more than 1 unit for each box, you can. So then on this other side, you want to repeat the pattern of going up and down and up and down. Make sure it looks like a wave and not a mustache. All right, the second one, identify the midline. Right here, this +1 is going to be where your midline is. So you are going to make your midline at 1. In this one, this 2 right here is going to change how far away you go from the midline. So we're going to go up 2 and down 2 from the midline. And then this negative in front means that instead of starting up high on the hill, we are going to start down low. All right, so that's a lot. So normally in cosine, we start at the very top of a hill. For this one, we need to start at the bottom of a valley. So we are going to go to our midline. Instead of starting at +1, because of this -2 right here, we are going to start down 2 from the midline. So 1, 2. Then at pi over 2, according to our mother function, we are on the midline. At pi, we are 2 above the midline, then back to the midline, and then 2 below. Okay, so here is our cosine wave. Tried to make it curved and like a wave and not like a zigzag pattern. Okay, the other side mirrors it. What kind of function has this kind of y-axis symmetry, kids? It's even. Good, class. And that's it for today. Hope you enjoyed it. And we'll see you next time. Hope you had a good Thanksgiving. Didn't eat too much and get sick.